Hello everybody, so this is the second video associated with chapter 2 of the statistical learning class. In the previous video, in the first part of chapter 2, we've introduced a simple prediction method called k-nearest neighbors, and then we went on discussing model selection principles which are related to in-sample performance and out-of-sample performance. So the main discussion point was to assess the proper degree of flexibility you should provide to your model, which was the parameter k in the k-nearest neighbors method, which defined how many neighbors should you use to make some prediction. You cannot only look at the in-sample performance, which is the prediction performance of your model on the same data on which you train your model, but you rather have to use a second data set, which was called the validation set, and assess the predictive performance on the second set to avoid any form of overfitting in your model. Okay, so you have to optimize the performance not on your training set but on your validation set, which contains observations that were never seen by the model during the training. So now we're going to discuss a bit of implementation issues with that. So if we want to have assess training performance and validation performance, then we need to have two different data sets. So a training set and a validation set. So in practice, it's not always easy to get two different data sets. So sometimes we only have one data set, but an easy approach would then consist in that case in splitting the single data set into two parts. So let's say we can take 60% of the observations randomly from the data set, put it in the training set, and we take the remaining 40% of observations within the validation set. So this is an example of how we can cope with that. Pick your single data set, split it into two by randomly selecting observations and then assigning these randomly chosen observations either to the training or the validation set. So this is one possibility, but an issue with that is that you lose many observations in that case. So first, you have 40% of the data which is discarded for the estimation. So you only estimate your model on 60% of the data, which does not maximize the use of your data to estimate the parameters of your model, for instance. Or the other issue is that your performance through validation MSE is only estimated on 40% of data points. So you have 60% of data which is discarded for performance evaluation. So that's a bit unfortunate, because when you try to either train your model or assess its performance, you'd rather like to have as many data as possible to have either parameter estimates or performance assessment that is as accurate as possible. So what we're going to do next, we're going to propose a way around this to ultimately use all observations, both in the training and in the performance assessment, but still evaluate the performance of our model out of sample, meaning that whenever we predict a response, the prediction for some observation, the prediction is only formed from responses of other observations. So you cannot use the response of a given observation to make a forecast for that observation. So the approach we're going to propose is called Kfold Crossvalidation. So how do we apply this method? Let's describe that now. So here we'll use small k. So in k nearest neighbors, we use capital K for the number of neighbors. So now to differentiate what we're doing in Kfold Crossvalidation, we're going to use lowercase k instead of capital K. So the Kfold Crossvalidation approach involves splitting our single data set into k subsets, and we're going to denote ni being the number of observations within the subset I, where I goes from 1 to k. So if you sum the ni's, you get n, the total number of observations in the entire data set. And here again, ni is the number of observations in the subset I. So then the Kfold cross-validation procedure follows the following k iteration. Okay, so you repeat the following procedure for all i's, where I go from 1 to k. Okay, so here I doesn't refer to the ID of the observation. I represents the subset of observations. So for iteration I, what we're going to do, we're going to pool all the observations from all subsets except the subset I. Okay, so, and this pooling of observation will serve as a training set with a number of observations n minus ni. So we take all observations except these from the ith subset. So the total number of observations we have is n minus I, and then we're going to train the model on this pool of data. Okay, by training, I mean form predictions or determine this f hat, which is an estimate of the prediction function as a function of features. Then we're going to use this the trained model on these pooled observation to derive predictions for each of the ni observations in the ith subset. Okay, so we use data from all subset except subset I to train the model, and then we use the trained model to make prediction on that subset I. Maybe I'll draw a picture here just to be clear. So here, let's say this is all data sets. Then let's say we have 3 subsets. So let's say we are in iteration 2. So the idea is we're going to pool this data and this data to train the model. Okay, so we take all observations for all subset except 2, and then so train, and here we're going to use 2 as the validation set here, where we are going to form predictions for all observations of the subset based on our trained model. And then for these predictions within subset 2, what we're going to do is we're going to calculate a mean square error for the ith sample, which consists in the following. So it's the MSC for the ith subsample is 1 over the number of observations in that subsample times the sum across all observations of that subsample of the square difference between the jth observation in subsample I minus its associated prediction. Okay, so you can see that you take an average of the square prediction error for all observations in that set, where the response, of course, it's the response of these observations, but the predictions are formed with yes, the covariates from that set, but the f hat, the prediction function, learned from all other subsets. Okay. So now for each subset, we're going to have a mean square error, and the final step consists in aggregating these mean square errors across all the subsets. So okay, we'll see that in a few slides, but before that, let's illustrate this case for k is equal to 4 subset. So here in iteration 1, we pull all observations except for the first subset, and we train the model on the all observations in subset 2, 3, 4. Then once we have that, we can make predictions for the first subset, and we use that as a validation set and come up with MSC1. Same thing for iteration 2. we pull data from all subsets except the second one. We train the model on all these other subsets that are pulled together, and finally we make predictions based on the trained model for subset 2, calculate the MSE for the subset 2, and etc. You do it for subset 3, subset 4. And what happens here is for every time, every iteration, the prediction errors made on the subset in orange here is really out of sample, because when we make predictions for these ones, the model is trained only on other subsets that are distinct from this one, so it only uses responses from the other subsets to make predictions. Here it doesn't use predictions as responses from this subset to make predictions here. Okay, so this is truly out of sample. You're not using the answer to come up with a prediction. These observations are really unknown once you've trained the model, when you've trained the model on other subsets. Okay, so for each of these MSEs, there are averages of out of sample errors. And then at the end, as we mentioned, we need to pool the MSEs across all subsets. So to pool them, well, you just take the average square error across all the observations in all sets. So how you do that, you sum across all the k subsets, ni times MSEI. So ni times MSEI, it's simply the sum of squared errors in subset I, and then you take an average across all observations from all subsets. So you have to divide these by n, where n is the total number of observations in the dataset. So here, this gives a mean square error, out of sample mean square error, based on the Kfold cross-validation. Okay. So in that case, if we go back to our previous example where we have our k nearest neighbors and we try to find the suitable value of capital K, which is the number of neighbors to use to form the best prediction, we would use capital K so as to minimize this total MSE here, which is an out of sample mean square error. Okay, so the capital K that is best would be to the one which minimizes this out of sample mean square error based on small k-fold cross-validation. Okay, so if you are able to minimize this, it means it's considered that your model has the best performance. Okay, so as we said earlier, I just want to make that point again because it's very important. Whenever we consider prediction error in one of the iterations, so in one of the folds, the jth response for fold I or subset I minus the prediction, so the prediction errors are really out of sample, because whenever we came up with this prediction here, this prediction involved calculations relying on data or on responses for all folds except the ith one. So this one does not rely on this response. Okay, so if you change your data set and you change this value in the data set, this prediction should remain the same. Okay, so the prediction here does not use the response here to come up with the prediction. So this is really out of sample. So because of that reason, using the mean square error, out of sample mean square error as the quantity to be minimized when deciding on your model or selecting the suitable amount of flexibility for your model, this will not lead to overfitting. Contrarily to training MSE, where the most flexibility would clearly always lead to the smallest mean square error. Okay, so now we talked about Kfold cross-validation with a small k. what are typical choices for the small k? So how to determine that? Well, there's no clear objective rule for that. So typical choices in practice are tenfold cross-validation. So you split your data set into 10 subsets to apply this procedure. Why 10? Well, it's a round number, so there's no really rule which says 10 is optimal or something like that. It's just it's a round number, so people tend to use that. Another very typical case, which is extreme, is to take small k being n. So each subset contains exactly one observation. So when you predict the response for one observation, you train the data on all other observations except this one. So this procedure, when k is equal to n and you have as many subsets as observations in your model, this is known as leave one out cross-validation. Okay, so leave one out cross-validation, it would be ideal in practice because it allows maximizing the use of your data when estimating the model, because when you train the model, you're able to train the model on n minus 1 observations, which is the most you can do if you want to have an out of sample prediction. So it maximizes the use of data when you do the estimation, but because there are n subsets, and if n is large, then you have n iterations to do, so you have to train the model n times. So if n is a million, well, you have to train your model a million times. So we see that for large data sets, this approach is often not practical. Okay, so leave one out cross-validation, it would be ideal, but in practice, it's often unfeasible for a reasonable amount of time, so it's not necessarily done in practice. Okay, so we've talked about cross-validation. So we illustrated the Kfold cross-validation, and we're now going to discuss analogous scheme called sequential validation, and this typically applies in a context where you have various data subsets, but there's a time order in this subset. So each of these subsets would correspond to time. So for example, subset 1 would be data in January, subset 2 would be data in February, subset 3 data in March, etc. So there's a time order in all the subsets. So these subsets are collected sequentially through time. Okay, so for example, if you're an insurance company, then you collect data on claims in January, then February, then March until December, and then January, and then the next year, etc. So when you do that, if you apply regular Kfold cross-validation, it would entail that to form some prediction, let's say you have subset I, you take subset I out to train your model, and you train your model on all other data. This would entail training your model on data sets that are prior in time to I and that are after I subset I in time, which is weird because in practice you never have access to future observations when you want to predict your observations at a given time point. Okay, so for that reason, we're going to alter the regular cross-validation to reflect this fact. Okay, so when we apply sequential validation, when we want to assess the performance on subset I, we're going to train the model not on all other subsets, but only on subsets that are prior in time to the subset I. Okay, so this is meant to be reflective of true practice, where when in practice, when you make a prediction at some point in time, you only have access to previous information, not future one. So in this case, each of the subsets, as we mentioned, they will correspond to some time period I. So when we're making out of sample predictions for an observation in subset I, we will only use the subsets 1 until I minus 1 to make the prediction. So we shall not use I plus 1, I plus 2, etc., because these are future observations with respect to time I. So in practice, we don't have access to them to make predictions. So when we assess the performance, we don't necessarily want to use them. Okay, so this illustrates the difference between regular cross-validation and sequential validation. So here, if you apply sequential validation with k subsets, or let's say k is equal to 4 periods, here's how it goes. You would have exactly 3 iterations. First iteration, you train the model on period 1 and assess its performance on the data for period 2. Then second iteration, you train this would give you MSE2. Then second iteration, you use the first 2 periods to predict your responses in the third period. Then third iteration, you would use the first 3 periods to predict your responses in the fourth period. And then for each of these periods, you would get a mean square error. And then at the end, you simply aggregate them to come up with a total MSE. Okay, so we see that it works pretty much the same. It's just that when, let's say, you assess the performance in the second period, you only use the previous period. You won't use the future periods, which gives a closer resemblance to what happens in practice. There's another variation of the sequential validation procedure, which involves using what we call a rolling window. So the idea here is when the data sets are, again, collected sequentially in time, when you have some data that dates too far back, sometimes it becomes irrelevant. So let's say you're trying to predict stock returns or something like that. You could, in theory, use previous returns as far back as you want in time, but maybe returns from the 1950s, they're not relevant anymore because the market was so different back then, so you don't necessarily want to use these data to train your model. So you only want to go like a limited amount of time in the past to train your model, because before that it's meant the data is considered irrelevant. Okay, so we can alter the sequential validation scheme to use only the last D subsets to construct your predictions for the next period. Okay, so let's repeat again another example. This would be a rolling window sequential validation where we use, again, k is equal to 4 subsets, but here let's use a rolling window of 1. So every time we use only 1 period to train the data instead of all past data. Okay, so if we do that, this is pretty much like a sequential validation, but except here in the first iteration, you train the model on period 1 and assess its performance on period 2. So this is exactly as we did before. Then in the second iteration, you only use period 2 to train your model and then assess the performance on period 3. Okay, so why is this guy not in blue here? Why don't we use this one? It's because we use a rolling window of 1, so we only use 1 period in the past to train the data. Okay, because 2 periods away, it's meant to be too far back in the past, so we say that it would not become relevant. So for example, if you're in the industry and you're trying to forecast something, you might have requirements to use the last 10 years of data every time you come up with a model. Okay, so in that case, data before 10 years, you want to discard it in your rolling window and your sequential validation approach. So here, this is why this guy is discarded. Then in the third iteration, you train your model only on the period 3 data because you use a rolling window of 1. So periods that are 2 periods away and 3 periods away from the validation set, you don't use them, and then it says the performance here. This gives you MSE 2, 3, 4, and then at the end of the procedure, you can simply aggregate these mean square errors to come up with a final MSE which gives you the performance. Okay, so here if you wanted to do that for the k-nearest neighbor procedures, you would do this sequence of iteration for every value of capital K. Okay, so you do all of these iterations for capital K is equal to 1, get a total MSE, then do all these iterations for capital K is equal to 2, then get a total MSE, etc. And then you would compare at the end the total MSEs for all values of capital K, and then select the capital K, which minimizes the total MSE. Okay, so this is great. This allows us to use out of sample performance estimation, but without necessarily losing observations when we either train the model or at least assess the performance of the model. Because let's go back here for, okay, this is not exactly true because the model is never assessed on the first period. But if we go back to the regular cross validation, we can see that for any data point in any subset, at some iteration, the performance is evaluated on this data. Okay, so here in this Kfold Crossvalidation, there's no observation that is left out from the performance assessment, and here all observations from the entire data set are used at some point or another into the performance evaluation. Okay, so this is in a sense that might be considered better than the original proposition, which involves splitting the original data into a training set and a test set, because this original approach involved discarding some data from the evaluation, where here in Kfold Crossvalidation, all the data from the original data set are used at some point to assess the performance. Okay. So now let's say we follow the previous procedure and then we select our most suitable K, which maximizes the out of sample performance or minimizes the out of sample mean square error. That's great. But now one final question is, okay, we found the best model, the best value of K, but what's our assessment of the performance of that model? Okay, so for the selected K, we'd like to know if we apply this model on some new observations, what would be the expected square error we would obtain in that case. Okay, so if there is a new observation outside the data set, the okay, so x0 and y0. So here x0 and y0, we're going to assume they're not in the training set nor the validation set. Okay, so it's totally new unseen observation. We like to know what's the mean square error we would make on that new observation without, which is outside of our data set that we use. So outside both the training and validation sets, or if we use a single set and cross validation outside of this original data set. If we think about that, it is very tempting to use the MSE total, so out of sample MSE total or validation MSE total associated with the capital K we chose. Okay, because if we use the previous rationale, the validation MSE is meant to reflect the performance of the model on unseen data during the training model. Okay, so you might think, okay, if you have a new observation, this is unseen data, so this mean square error MSE total already reflects that, so we should use that to as our performance assessment for if we have new observations. In practice, sometimes it's deemed reasonable, but it's not 100% theoretically correct, because MSE total is typically a biased estimator of the expected square error. And by biased, I mean it undershoots the mean square error. Okay, so I've wrote biased, but maybe I should have written like downward biased because it's in average, this should be a bit smaller than the true mean square error for new observations. So why is that the case? Why is that biased? Well, it's because since the validation set is used to select the optimal parameter k, in some sense, it becomes part of the training set because you've used this uh, new data set to select one parameter for the model. Okay, so and the selection was done so as to minimize the errors in the validation set. So once again, if we had a validation set with an infinite number of observations, maybe we would not have this problem. But in practice, the validation set has a finite number of observations. It has some noise. So the optimal k we chose is impacted by the noise in the validation data set. Okay, so the optimal k we obtain in practice, because the validation set has finite dimension, it's only an estimated value of the optimal k. It's not necessarily the true optimal k. So for that reason, there might be a bit of overfitting to the validation set still. So please take some time to think about that, because now this becomes a bit abstract, but please take some time to think about this. So the MSE total typically underestimates the expected mean square error for a totally new observation, because your estimated optimal parameter k could be slightly incorrect due to some noise in the validation set, and might have been chosen so as to since it has been chosen so as to minimize the MSE total, then that MSE total might be a bit smaller than the true value just out of randomness, okay, which would be overfitting the validation set. So because of that, MSE total is not necessarily the correct thing we should use to assess the performance on totally new observations. So if we want to do that, the solution, if we really wanted to have an unbiased estimate of the expected square error we would obtain on a totally new observation, the solution would be to use a third data set which contains observations that are neither in the training set nor the validation set. Okay, so this third data set, which is presumably independent from the training and validation set, is known as the test set. And then to really assess the performance on totally new observations, you need to what you can do is take the mean square error of predictions made for this totally new data set. Okay, so you use the model where k was selected based on the validation set, but once you know k, you can train your model on the entire data set, or the training set. It's up to you, either training or training plus validation. You use this trained data to predict values or responses for the third completely new data set, and then take the average of squared prediction errors, and this should be an unbiased estimate of your mean square error for your model you've estimated. Okay, so in practice, if you wanted to be fully rigorous, you need three data sets. First data set is a training set, which is used to estimate or determine your predictions. And what do we mean by that is to come up with an F hat. But that F hat depends on some flexibility parameters, which are often referred to as hyperparameters. So in the k nearest neighbors, the hyperparameter was the capital K. So then to determine this capital K, which is the optimal, the suitable level of flexibility, then you need a second set, a validation set. So training is used to get f hat. Validation set is used to determine capital K. And then the test set is used to assess the mean square error for the optimal model based on estimation from the two first data sets. Okay, so we said we need three models, but we can three data sets if we want to be rigorous. But in practice, often we can save one. So if we use Kfold Crossvalidation, we can use only two data sets, okay? Because we can have a first data set that you can split into subsets and apply the cross-validation procedure to come up with, for example, your optimal value of capital K and your predictions or the prediction function f. And then based on these, which were only obtained in a single data set on which you applied cross-validation, then you can make predictions for the second data set, which would act as the test set. And then on this test set, you can compute the mean square error to assess the performance of your model. And then you wouldn't have a biased estimate of the mean square error because these are totally new observations that were not used during the training of the model. Then you would have an unbiased assessment of the mean square error of your model. So that completes the material for chapter 2. We'll then skip to go to chapter 3 next, where we're going to discuss some more regression models and estimation, prediction concepts. All right, so thank you. Have a nice day.